Welcome to discussion 11. In today's discussion, we'll focus on sections 2.7 and 2.8 on the definition of a derivative and 3.1 on derivative rules. In this video, we'll focus on graphical derivative questions. So I want to look at problem number 4, parts A, B, and D from worksheet 5, which I have copied here. So it says, for the graph below of y equals f of t, representing the position of a particle in feet at time t in seconds, please answer the following questions. So I want to focus on part A, B, and D in this video. And first, I want to give you 7 minutes to try these. So 4, 3, 2, 1, pause the video, pause it for 7 minutes to try A, B, and D. Alrighty, so hopefully you did that. Hopefully you paused it for about 7 minutes to try those collectively. Let's talk about it together. So A is asking us to estimate the instantaneous velocity. Instantaneous velocity. So remember that instantaneous velocity, instantaneous something is a derivative, and velocity is the derivative of a position function. So this wants the derivative of the position function. I'll just write func for function. But the position function is y equals f of t, this graph that I'm given here. So the velocity, instantaneous velocity, should be f prime of t. And graphically, the derivative represents the slope of the tangent line. The slope of the tangent line. And notice I wrote f prime of t and not f prime of x, because in my function, it's writing f of t and not f of x. So for this question, part A, it wants the instantaneous, let me just abbreviate, instantaneous velocity at t equals -1, which means we want the slope of the tangent line. At the point where t equals -1. Okay, so if I go to the graph, and at t equals -1, if I draw a point, I have this. So there's a few different ways I could draw a tangent line. One is, because it just asked me to estimate this instantaneous velocity, I just want to estimate the slope of the tangent line. So one thing that I could do is I could pick a nearby point, any nearby point, I could connect them with a secant line, and I could just find the slope of that secant line. I could also just, kind of eyeball it and draw a good tangent line. That's what I'm going to try to do. So a tangent line might be something like this. It's got to match how steep the graph is right at that point. So that is a tangent line. And it seems like my tangent line, goes through, if I go 1 unit this way, it goes through a point that's pretty close to 5 units up. Okay, maybe it's a little bit less than that, but it's an estimate. So let's use that. Okay, let's actually go a little bit up so I can still see the picture. So if I use rise over run, okay, the rise going from this point to that point is sort of going down 5 units. So I'll have -5, and the run is 1, so I'll get -5 over 1. And there's units here, the units of y, of my position, are feet, and the units of x, in this case it's t, of time, are seconds. So it's in feet per second. Okay, and if I simplify this, this is -5 feet per second. And actually, maybe it would have been better to put an approximately equal to, because I am estimating the slope of this tangent line. And there we have it. Okay, we are on to part B, which is larger f prime of -2 or f prime of -1. Well, we know derivatives are slopes of tangent lines, and f prime of -1 we already got. This is the slope of the tangent line at the point where t equals -1, and I could see that from the picture. We've already drawn that one. So let's talk about this other one, f prime of -2. This is going to be the slope of the tangent line. Slope of the tangent line at t equals -2. Okay, so if I go to my graph and I draw a tangent line at t equals -2, so here's the point on the graph. So it looks like at -1, my graph is pretty steep. And as I go closer and closer and closer to -2, the graph gets flatter. So I should be drawing a tangent line that is flatter than my purple line. Okay, so not a perfect picture, but something like that. Okay, so slope of my tangent line at t equals -2. This slope, this line, this is not as steep. This is not as steep, so the slope is, because both of these slopes are negative, and the orange one is less steep, that means that slope is, in quotes, I'll say it's less negative. So what do I mean by less negative? Well, the slope of the tangent line at t equals -1, we already estimated that in the previous question. It was approximately -5. And because this other tangent line at -2 is not as steep, it's going to be less negative. What I mean by that is it's maybe going to be something like -3 or -2 to indicate it is not as steep. So as a number, that means f prime of -2 is a bigger number. Okay, because it's kind of like we're comparing, maybe f prime of -2 is -3, and the f prime of -1 is -5. Clearly, the -3 is a bigger number than -5. All right, and then finally, let's look at part D of this example, which is asking us to estimate the times when the particle momentarily stops. Okay, so the particle is going to be stopped when the velocity is 0. Okay, stop when the velocity equals 0, but we know the velocity is the derivative of position. So when f prime of t equals 0, and we know that the derivative is just the slope of the tangent line. So we're looking for when the slope of the tangent line is 0. So when does that happen? This happens at, we want to know when the slope of the tangent line is 0. That's going to happen at points where the tangent line is flat, it's horizontal, when the curve gets kind of momentarily flat for a split second. So that happens here at this bottom point, right? Because if I were to draw the tangent line, it would be perfectly horizontal. The graph is flat there. Okay, it'll happen here. The graph gets momentarily flat. It'll happen again at this bottom point, and then it'll happen again at this high point over here. So the question asked me to estimate those times because some of them are not they're not like perfect integers. So the very first number seems to be a little bit less than -2. So maybe I'll write it's something like t equals -2.2. And then if I go to my graph, that next point seems to be t equals 0. And the one after that seems to be t equals 2. So let's just write those down. So t equals 0 and t equals 2. And that last one seems to be in between 3 and 4, but maybe slightly closer to 3. So maybe I'll say 3.4. And the units of time are seconds. And of course, because I was estimating, if I was slightly off with any of these, that would be fine. So in particular, -2.2 and 3.4, they're just estimates. It's okay to be a little bit off from what I wrote. All right, I want to look at another example. This is problem 5 from the same worksheet. And I have this graph, same graph, but now it says, now suppose this graph is the graph of the derivative. So we are now assuming that this is the graph of the derivative. The derivative, so this is y equals f prime of t now. All right, so first I want to give you 4 minutes to try this question. So pause it in 4, 3, 2, 1. Pause that video and try it for 4 minutes. Alrighty, so hopefully you did that. Hopefully you paused it and tried it for 4 minutes. Let's talk about it together. And part A says we'll estimate the instantaneous velocity at t equals -2. So for A, we want to find the instantaneous, I'll abbreviate, velocity at t equals -2. So we know that that is going to be the derivative, f prime, at -2. But now, this isn't the graph of the original function. It's the graph of the derivative. So I need to know, well, what is the output of this derivative when I'm plugging in -2? So I'm just going to look to the graph where, the t value is -2, and that's here. And I'm just looking for the y coordinate. That's the output of the derivative. Okay, and that's something between 6 and 7, maybe a little bit bigger, a little bit closer to 7. So maybe I'll say this is about 6.6 maybe. And units of velocity in this question were feet per second, following the units from problem 4. Okay, so there we go. All right, let's do part B. B says, well, when is the particle now momentarily stopped? So it is stopped when the velocity equals 0. Okay, and the velocity is the derivative of position f prime of t. We want to know when f prime of t equals 0. Okay, and because this is the graph of f prime of t, we want to know when its y values, its outputs equal 0. Okay, so looking at my graph, I can see that that's going to happen here at -3, at -1. It seems to happen at 2, and also at 4. So let's write those t values. We get t equals -3. We get t equals -1, 2, and 4. And the units are seconds. And that is our answer.